Hi everyone! New applications impose increasingly stronger requirements on network performance and reliability. As a result, network operators deploy more complex traffic engineering. One mechanism that enables fine-grained traffic engineering is to tag routes with BGP communities and then use these tags in the route selection process. However, networks on the internet can define BGP communities however they want, and thus it is hard to understand the meanings of communities and effectively use them. In this work, I'm going to show you how we can automatically infer communities that correspond to physical locations and devices, which can help network operators deploy traffic engineering and researchers extract route properties. This is joint work with my colleagues Paulo, Osvaldo and Italo from UFMG, Ronaldo from UFMS, and Ethan from Colombia. The Internet is composed of autonomous systems that exchange reachability information using the Border Gateway Protocol. To grant Internet reachability, operators rely on BGP's best path selection algorithm. Although BGP has been around for more than 20 years, its flexibility has allowed network operators to express their routing policies to cover most of the modern network requirements. However, the growing need for reliability and performance have led to more dynamic and complex routing policies stressing BGP and exposing the limitations of the protocol. Operators use many knobs provided by BGP in the pursuit of expressing routing policies. Local preference, import and export filters, and BGP communities are some of the more common knobs. To overcome the limitations in BGP expressiveness, network operators have relied more on the optional BGP communities attribute to convey information in their routing announcements. BGP communities are a transitive attribute on BGP. A community is a tag generally expressed by an AS number followed by 16 number and do not have any innate semantic that expresses its meaning. A community is essentially a tag used to carry information between routers. The meaning of the community is defined by the operator and can change from one NS to another, encoding information such as the city where the route was learned, the business relationship with the neighboring network, or requests for actions such as BGP prepending or targeted route filtering to improve the user experience. A location community is a community in that a router tags to an announcement to let the other routers know from where to pass. Let's look at an example and explore specifically the idea of communities being used to tag locations. Here we have an operator on ESV that uses a location community to control route selection. The origin ASO announces prefix to ASA at locations L1 and L2 and to ASB at location L2. ASA tags routes received at L1 and L2 with communities AL1 and AL2 respectively. Then, A announces its preferred route to V. So V receives one route from A tagged with either L1 or L2. And V also receives an announcement of the prefix from B. Consider that V has a policy that routes learned from B should have higher priority than routes learned from ASA, for example, because B's transit costs are cheaper than A's. However, ASV may decide to use routes received from ASA that traverse L1, for example, because they have much better performance that justifies the higher cost. To implement this policy, V sets preference to 120 in all routes received from ASA with community L1. Sets preference to 100 for routes learned from ASB, and sets preference of other routes to 80, including routes from A tagged with L2. As BGP uses local preference as the first criterion to decide the best route, V selects the high performance route from ASA when it's available, and the cheaper route from ASB otherwise. Routes from ASA with tag L2 are chosen only when no route is available from B, for example, due to failures. We also have other communities with other semantics, for example, communities to change how announcements propagate, which are useful for tasks such as traffic engineering and troubleshooting. One problem, unfortunately, is that each operator is free to define any semantics for its communities. There is no standard describing what semantics are supported or how they should be documented. The result is that different operators support different semantics that are documented in different places following different conventions. To make matters worse, some ASs handle communities in non-intuitive ways or violate conventions. For example, operators may have questions such as, what community can I look for to check if a route traverses Boston? Is the documentation reliable and up-to-date? How do I know if these routes traverse LA or New York? where's the documentation on the communities in the announcements? Given our lack of visibility over internet routes, it is hard to identify that a route actually traverses the location indicated by the communities, and even harder to identify a community whose semantics does not match the documentation. What do we have right now to help operators and the communities with this situation? Researchers from CADA created a tool that performs web mining for analyzing data from Internet Route Registry and web pages using natural language to determine the semantics of communities and pinpoint outages. As his work depends on public documentation, the failure in identification accuracy is a function of how accurate the community information is. Other researchers created a community inference engine, but with a different goal than ours. It does not determine the semantics of communities, but whether AES is inserted or removed community tags in a route. Another work tries to identify black hole communities and show that some AESs use different values. However, operators create and document new communities over time, so we need to keep updating our databases. Also, operators handle communities by hand, searching for the documentation in registries and websites, and then looking at the available communities and testing them to check if their effect matches their expected behaviors. It's hard to identify the semantics of communities, so we focus our work on inferring location communities to help operators to improve their efforts on traffic engineering. Now, let's explain our algorithm for inferring location communities in detail. We propose an algorithm to automatically infer location communities from public route announcements observed by BGP route collectors like route views and race. We use BGP route collector peers as vantage points. Consider a target AST that tags received routes with location communities. If T and N1 interconnect at a single location, then T will tag all routes received from N1 with the location community corresponding to their single interconnection. One idea is to identify communities that appear in all routes from N1 traversing T as a candidate location communities. Unfortunately, we don't know how many interconnections a pair of ASs have. When AST and ASN2 interconnect at multiple different locations, T may choose routes received from N2 at any of these locations. Each chosen route will have a different location community corresponding to the interconnection where it was received. For example, we will tag routes received from N2 over the blue link with L2. And we will tag routes received over the other link with L3. But no community will appear in all routes, and no location community will be inferred. It is challenging to infer the number of interconnections between two ASs, and so we don't want our approach to rely on that information. As we have multiple links, each location community will appear in a subset of routes from N2 traversing T. The key insight in our algorithm is to use interconnections between ASs as landmarks and identify location communities as those correlated with a fixed set of landmarks. Suppose that AST and ASN3 interconnect at multiple locations and that T receives multiple routes with AS paths traversing N3, N4, and N5. Given a sequence of announcements collected and traversing the AST, we capture all announcements and create an aggregation of the multiple announcements that use the same AS path. From the announcements of N6, N7, and N8. We observe the non-empty sequence of ASs constraining the locations where T may receive a BGP announcement as beta, the gray region in the figure. So let IT3, I34, and I45 be the interconnections traversed by the routes. Interconnection IT3 is constrained by the set of interconnections between AST and N3 and by their routing policies. Also, interconnection I34 is constrained by the interconnections between ASs N3 and N4 as well as their routing policies. And the similar constraints apply to I45. For each relationship between ASs, we believe that the restrictions will be respected regardless of the origin AS. This is just the general idea behind the algorithm. We invite you to check our paper for additional details. Our inferences use the property that AST will receive routes traversing N3, N4, and N5 at few locations, possible a single one. If a community T from T appears in all routes traversing N3, N4, and N5, then we consider it as a candidate for inference as a location community. Let's take a look at our ground truth database, dataset, and evaluation. We manually built a database from all Tier 1 and 2, from which we found a database of BGP communities. Some ASs describe rules to generate the interval of communities that are used for specific types. For example, GTT uses an interval that can encode up 10,000 geolocation communities. On the other hand, Lumen uses a combination of the CountNet and the Country code to generate its communities. We break informational communities into those that identify a geographic location, a device or a link on a router, or a peering relationship. And we also identify action communities. We consider as location communities the geolocation communities as well as devices or link communities. These are the communities our algorithm tries to infer. We also show the number of communities from the AESs in our database in CADA's Geographic Location BGP Community Database from April 2019. We collected the BGP feeds from 3 different projects: RouteViews, Riperies, and Isolario. The table shows a summary for the route table dumps from December 2017 and 2020. Unless specified otherwise, we use the first available route table dump from each BGP route collector on December for each year. And we use the only BGP RIPs to process these table routes. The number of collectors do not change so much, but the number of vantage points increased by 21%, the number of AESs increased by 18%, and the number of routes almost doubled, increasing by 91%. We report precision and recall and show how they can be prioritized by tuning the configuration of our algorithm. We also quantify inference accuracy with precision and different views of recall. In our work, we present 3 configurations to prioritize precision or recall during the inference process. Our technique has 3 parameters that control how conservative or aggressive it is when inferring a community as a location community. These parameters can be set to prioritize precision in a conservative configuration or prioritize recall in a more aggressive configuration. As we can see, the precision is high, but the recall drops as our filters remove some of the correctly inferred communities lacking route diversity. And we also report the Invariable Recall, which considers only communities that appear in enough paths and are actually considered for inference by our algorithm. In this case, the recall is a little higher. So if we have enough data, in other words, more collectors or a technique, we'll get a more complete view of location communities in the internet. We compare our results of location and geolocation with the CADA database when possible. The table shows statistics for geolocation communities in both databases, the first rows. We use 2 rows here because CADA only has geolocation communities, and we get all of them bundled in a large set. So it's hard to compare CADA's database directly with your results. And for location communities in our database, last row. We compute recall of geolocation communities considering only the subset of geolocation communities in the ground truth database. We do not compute precision in the number of geolocation communities for our inference algorithm, as it does not differentiate between geolocation and location communities. We find that CADA's database has high precision, but not 100%. Investigation of incorrect inferences indicate they are concentrated on Tier 2 AESs and explained by reassignment of community values, which motivates our automated inferences. Also, CADA's community database has limited recall, which is somewhat expected for a manually built database. Our inference algorithm achieves significantly higher recall than CADA's database even for geolocation communities. Let's take a look at a figure that explores the relationship between the number of constraints, precision, and recall. We show in figure 1, 2, and 3 constraining AESs and relate it with the precision and recall. Look at the figure, we see the impact of the number of constraining AESs after T in the AES path when making inferences. In other words, the size of beta. So, more constraining AESs limit the set of locations where chosen routes arrive at the target AST, leading to higher precision. However, AES paths in the internet are usually short, and there are fewer long AES paths to support inferences with long sequences of constraining AES, which limits recall. We consider all sequences with at least one constraining AES. Our algorithm can be configured to require more constraining AES, which will lead to higher precision at the cost of recall. In our paper, we evaluate the impact of other 2 configuration parameters and show that the accuracy and recall are not significantly affected by their values. We also investigate the impact of route visibility on BGP collectors on community inferences. We rank route collectors on the x-axis by picking the collector that support the most inferences, and then greedily selecting collectors by the number of new community inferences they support. The blue line shows that we have diminishing returns as the number of collectors increase, but the tail is somewhat long. We also observe that some collectors have visibility to a lot of communities but could contribute just a few new communities. This happens because overlap across collectors. We see that some collectors observe few communities but support a relatively high number of new inferences. This indicates that strategically placing collectors could improve route visibility and community inferences, so additional collectors will support more inferences. In conclusion, in recent years, the use of BGP communities has increased significantly. As routing policies have become more complex and performance requirements have become more stringent on the internet, network operators have to deploy increasingly sophisticated traffic engineering solutions. Unfortunately, there is no standard for specifying semantics nor a centralized repository that catalogs BGP communities, which complicates their use by network operators and researchers. Our work is a first step towards automatically inferring the semantics of BGP communities. Our algorithm infers location communities and achieves high precision in recall. And our manually built ground truth database as well as the code to generate the location database are publicly available. Thank you.